And welcome back as we continue our cosmic journey. Let's go ahead and veer away from Earth now to go ahead and look at our nearest neighbor, which is that of the Moon. And let's start off by just looking at a couple general properties of it. So when we start talking about properties of the Moon itself has about 1/18th of the mass of Earth and about 1/6 of the Earth's surface gravity, which is too low for it to retain an atmosphere. Moving molecules of a gas can easily escape from a planet just the way a rocket does, and the lower the gravity, the easier it is for the gas to leak away into space. Now, while the Moon can acquire a temporary atmosphere from impacting comets, this atmosphere is quickly lost by freezing onto the surface or by escaping into surrounding space. The Moon today is dramatically deficient in a wide range of volatiles, and those elements and compounds that evaporate at relatively low temperatures. Now, the Moon does have two sides to it. The left image shows the part of the hemisphere that faces Earth, because remember, the Moon is always tidally locked, so we're always going to see the same side of it. And here we can see several dark Maria. The other side, of course, is the part of the hemisphere that faces away from the Earth. It is dominated by what we refer to as the highlands. Now, the resolution of the image is several kilometers, which is much like if you had high-powered binoculars or a small telescope. So you can get a lot of good detail if you were to go and actually zoom in on these images right here. Now, with the Moon, of course, we'd love to do exploration on the Moon because we can get a lot of information about it and really learn about our cosmic neighbor. Most of what we know about the Moon today actually derives, though, from the U.S. Apollo program, which sent 9 piloted spacecraft to our satellite between 1968 and 1972, landing 12 astronauts on its surface. Before the era of spacecraft studies, astronomers had mapped the side of the Moon that faces Earth with telescopic resolution of about 1 kilometer, but lunar geology hardly existed as a scientific subject. NASA targeted geologically interesting locales with successive missions. Now, the level of scientific exploration also increased with each mission. So the astronauts would spend longer times on the Moon, and they would carry much more elaborate equipment in order to gather more interesting data. Now, when we start talking about scientists on the Moon, we did learn a lot of things here when they actually visited. In this image at right, you got geologist Harrison Jack Schmidt in front of a large boulder in the Littoral Valley at the edge of the lunar highlands. You'll note how black the sky is on the airless Moon. That's not just some bad image properties there. It's literally just the blackness of the sky. And another thing you'll note is in that black sky, no stars are visible. Because one thing to keep in mind with the Moon is that the surface is brightly lit by the sun, and the exposure, therefore, is not long enough to actually reveal any stars. Now, when we start talking about the Moon, we can talk about the impacts that we've had on it. In addition to landing on the lunar surface and studying it at close range, the Apollo missions accomplished 3 objectives of major importance for lunar science. First off, the astronauts collected nearly 400 kilograms of samples for detailed laboratory analysis on Earth that revealed as much about the Moon and its history as all the other lunar studies combined. Each Apollo landing after the first also deployed an Apollo lunar surface experiment package, which continued to operate for years after the astronauts themselves departed. And the orbiting Apollo command modules carried a wide range of instruments to photograph and analyze the lunar surface from above. So if we start looking at the composition of the Moon, this is again one of those things that we learned from those studies on the Moon's surface. We found that the composition of the Moon is not the same as that of Earth. It might be similar, but is not the same. In fact, we found that the Moon must be made almost entirely of silicate rock. Compared to Earth, it's depleted in iron and other materials. It's as if the Moon itself were composed of the same silicates as Earth's mantle and crust, with the metals and the volatiles selectively removed. So we have some, again, we're similar, but it's not the same. These differences in composition between the Earth and Moon provide important clues to us about the origin of the Moon itself. So let's look at some of those materials and really kind of analyze what that means. Well, studies of the Moon's interior carried out with seismometers taken to the Moon confirm the absence of a large metal core, unlike the Earth, which has a core of largely nickel and iron. We also know from the study of lunar samples that water and other volatiles have been depleted from the lunar crust. The tiny amounts of water detected in samples were originally attributed to small leaks in containers sealed that emitted water vapor from Earth's atmosphere. However, scientists have now concluded that some chemically bound water is present within lunar rocks. Most dramatically, water ice has even been detected in permanently shadowed craters near the lunar poles. So let's talk about that ice just for a second here, because this does have some implications for us. The total quantity of water ice in the moon's polar craters is estimated to be hundreds of billions of tons. Presumably, this polar water was carried to the moon by comets and asteroids that hit its surface. One of the reasons why this discovery could be important is that it raises the possibility of future human habitation near the lunar poles, or even of a lunar base as a way station on routes to Mars and the rest of the solar system. If we could mine that ice, it would yield to us both water and oxygen for human support, and it could be broken down into hydrogen and oxygen, which of course would make for a potent rocket fuel.